So if we take a look at the titration that we're describing here, we have the ascorbate ion. It's C6H6O6 2 negative. Sometimes some of these large compounds that have carbon in them won't be written in a summed up fashion, but rather they'll be written as a bunch of carbons with hydrogens attached to each of them. So just be cautious when you're looking at anything that has a bunch of carbon in it, what it might actually be, because sometimes we might ask you about the structure. The ascorbate ion is a base, so our initial pH would be on the basic side. As we continue to add more and more HCl, which was our titrant, the pH would start to decrease. Now, not a ton at first, because remember at first, there is way more hydroxide than there is hydronium, and it can neutralize it. We would see one endpoint, then another. Now, sometimes what you have to do is figure out what's the pH of the endpoint, or what's the equivalence point. But sometimes what you have to answer is, what's actually present? What reaction happened to cause this particular curve? So if I consider what's going on up here, I know I have ascorbate, and I'm adding hydrochloric acid. And since hydrochloric acid is a strong acid, it's like I'm adding hydronium, right? I completely replaced it because 100% of a strong acid ionizes and becomes hydronium. I would show that the acid, the hydronium, donates a hydrogen to the base. And I would recognize that once I do the first part of the pH curve, so the first drastic change has happened, that proton has been transferred. So remember that this section means proton transfer. I've seen that show up in exam questions, like what does the sharp change on a pH curve tell you in terms of what has happened? And it tells you that a proton has been transferred. That means that you would have C6H6O6H negative, right? I added a hydrogen to it, and water as the product. That's my first reaction. If I continue to add more titrant, I'll take this substance here and I'll add more hydronium. So I'm using the product of the first reaction as the reactant for the next step. The same thing happens. Hydronium donates a hydrogen. And I'm left with, in the end, these two things, where I have my original base that had a 2 negative charge. It gained one hydrogen in the first section and another hydrogen in the second section. Anytime you can see that there are two endpoints, or the question tells you that there are two endpoints, what it's really telling you is that two protons were transferred. It means that one of the substances was polyprotic, meaning either the base could accept more than one proton or the acid could donate more than one proton. In the case of hydrochloric acid, it doesn't have more than one hydrogen. But in the case of that base, because it was -2, it could accept more than one proton, one the first time and another the second time. Now, does anyone want to ask anything there? Okay. So today, we're going to add to this whole idea of pH curves buffers. All pH curves, all of the ones we've looked at, have at least one region where the pH remains relatively constant despite the continuous addition of titrant. It's a flat section on a pH curve, and it's called a buffering region. So in addition to what we already know about pH curves, we're just adding one more idea. Now, if you look at the pH curves that are on the whiteboards, I think you would all agree most of them have two flat sections. So how do I know where the buffering region is? Well, it's where the titrant volume is halfway to the first equivalence point or halfway between any other equivalence points. Now that helps me decide which flat section is a buffering region or not. So if I look at an example where I'm titrating a weak acid with a strong base, I would expect my pH curve to look something like this. Now, because it was a weak acid with a strong base, let's pretend right about here is 7, but my endpoint is about there. I made my endpoint be higher than 7, because that's what you see when you have a strong base but a weak acid. On this graph, the equivalence point is right about here. So the description said that halfway to the first equivalence point, half that volume of titrant, that is where we have a buffering region. So if I look down here, we'll go right about here. This is about halfway. That means right about there, which conveniently is in the middle of that section that's not changing a lot. Notice it's not perfectly flat, and buffering regions will not always be perfectly flat, but it's not changing a lot. This section is a buffering region. Now, if we consider what's happening here, remember I'm adding NaOH, and I'm adding it to my weak acid. So if I think about at the beginning, what's present? I have my acid. As it reacts, eventually I know that when I get to my end point, I should have its conjugate and water. But when I'm not all the way there, not all of it has reacted. When I'm in this buffering region, only about half of that acid is reacted. So I started out with this acid, and when I get to that buffering region that's about halfway to the equivalence point, I haven't used up all the acid. Only about half of it has reacted. The half that has reacted has made this conjugate base. So if I consider the reaction that's happening, I'm adding sodium hydroxide, so hydroxide ions, and my acid is donating protons to the base. But it's only half done. So what I have is I have a solution that has about half of the acid and about half of the conjugate base. So in this buffering region right here, because of that scenario, I have roughly equal amounts of weak acid and conjugate base. Right? Because about half of my acid has reacted, and I know when it reacts, it's going to make its conjugate base. Now, does anyone want to ask any questions about what is happening in that buffer region right there? Now, if I take that buffer that I have, so if you look at the reaction that's there, this is the one that we just looked at. Here is a weak acid. Here's the weak base. If I did the titration that I said that I just did, I would have, in that buffering section, this basic solution. Now, if I add a strong base to a solution that contains both of those conjugates, the weak acid donates a proton and those hydroxide ions get neutralized. So when I have a weak acid and a weak base both present at the same time, they can neutralize things. Now this only works for small amounts. If I have really large amounts of hydroxide ions, it's going to overwhelm my weak acid. But in small amounts, this base can be neutralized by a buffer. If I consider the reverse, what happens if I add an acid to this same system? Notice how the reaction is written here. Instead of writing the acid as a reactant, I wrote the base as a reactant. They're both present, so either one of them can be a reactant. If I add a small amount of hydronium, it can donate a proton to that base. And what's left? The hydronium is neutralized to water. Now, what's really, really important here is the small amount idea. I can't add large amounts. For a buffer to work, it can only neutralize small amounts of acid or base at a time. If you overwhelm the system, there's not enough reactant molecules to neutralize everything that you're adding. So, what is a buffer? Like I showed you on the pH curve, it's when I have conjugate acid and base pairs in roughly equal amounts. It's usually about halfway to the equivalence point on a pH curve. And the reason the pH isn't changing is because I have both an acid and a base present. They could neutralize acid or base as it gets added to the solution. Now, does anyone want to ask anything about that? Now, why would you even care about a buffer? Well, like a lot of chemistry, your life depends on it. You are alive because you have buffers. For example, a lot of processes that happen in your body require a specific pH level. If you remember in Bio 20 learning about enzymes, if you took bio, some enzymes work best when the pH is low, like the ones in your stomach. Some enzymes work best when the pH is higher, like the ones in your intestines. A lot of cell metabolism is buffered by the H2PO4 negative and HPO4 2 negative buffer. The buffer system that's in your blood, which maybe you might remember hearing about, is the carbonic acid and bicarbonate buffer system. You get that from CO2 that comes from your cells during cell respiration. Now, this particular buffer maintains the pH at a pretty specific value. Does anyone know what the pH of your blood is supposed to be? 14 is a bit high. The people who said 7 and 8 were the closest. 7.4 is about where the pH of your blood is supposed to be. If you didn't have this buffer in your blood, so this system of weak acid and weak conjugate base, they can neutralize acid or base as it comes into your bloodstream. But without this, you could drink a glass of orange juice, which is quite acidic, and have the pH of your blood drop drastically and rapidly. But because you have buffers, you can consume foods that are acidic and not have the pH of your body be instantly changed. Now, does anyone want to ask anything about that? How much orange juice? It would depend on your body size too. Like we'd have to do a mass calculation with the LD50 value for those things to see. So a lot, like a lot would be the answer. Don't drink vinegar. You'll probably burn the inside of your digestive tract. Yeah. Sorry, I can't hear his question. It would apply the same way for bases. So the reason I talked about acids is because most of the food that you consume is acidic rather than basic. Basic things tend not to taste very good. So generally the things that you eat are not basic. If they are, they're only very slightly basic. Things like soap are basic, and I don't think a lot of you eat that. Sorry, I still can't hear because everyone's talking. So you guys are only thinking about pH at this point. Remember that if something is corrosive, it might not make it to your bloodstream because it might eat away at the sensitive lining on the inside of your digestive tract before it makes it that far. So I wouldn't do that if I were you. Now, one more question and then I want to show you this last example. Go. I'm going to go back to my same statement before. Besides the pH, there are other reasons that that's bad. For example, toxicity to cells, damage to the cells themselves, and the integrity of them. So remember, pH is just one thing that's happening inside your body that's keeping you alive, but the cells have to still be functional and not destroyed. Okay. Now, one thing that you might need to do is calculate the pH of a buffer using a Ka expression. And you need to be careful because it will be slightly different than all of the other times we have used a Ka expression. I have a buffer solution that contains HF and F negative. Now, normally when I write out an expression for an acid, for a weak acid, I say I take my acid, I put it in water, and I get hydronium and my weak base. It's no different when we're talking about a buffer because we're going to use the Ka expression. That's why I put the acid first here. If you knew the Kb value, you could write it as a base solution producing the conjugate acid. The difference is when you make a buffer, you don't just put the acid in water and hope for the best. You specifically add to the solution both the acid and the conjugate base. If I didn't do that, I would never have approximately equal quantities of both of them. So remember, the key with a buffer is that these two should be approximately equal in concentration. So it says right in the question, 0.28 moles per liter of this and 0.26 mole per liter of that. Now, when we just took a weak acid and put it in water, we always assumed that the conjugate base and hydronium had the same value. This isn't the same. I didn't just take a weak acid and put it in water. I took some weak acid and some weak base and put them both in the solution together. So this value here is not the same as that weak base. And it's because I didn't just let this happen. I purposefully put both things that are part of this reaction together at specific concentrations. Now, if I think about what the Ka expression would be, products always on the top, reactants on the bottom. Now, I'm leaving out water. Can someone remind me why I leave out water? Because it's a liquid, and I only include them if every single thing is a pure liquid. All of the others are aqueous, so they get to be part of Ka. Now I want to know the pH of this solution. So I know to do pH negative log concentration of hydronium. If a diploma question asks you what's the pH of something, and you think, oh, I don't even need to do anything, they gave me hydronium in the question, you're probably wrong. Don't do that. There usually is a step prior to that. Here, we're going to find the concentration of hydronium and then use it to calculate the pH. Now, how am I going to find hydronium? Well, I know Ka. Ka in the data booklet is 6.3 times 10 to the power of negative 4. I looked up Ka for the weak acid because that's the expression that I wrote. I know F negative 0.26, and I know HF 0.28. Remember that the K expression is always equilibrium concentrations. In this case, that's what we have, but you might remember that sometimes we assume that at equilibrium so little has changed that we can use the same value. If I simplify this and find the concentration of hydronium, I end up with 6.78 times 10 to the power of negative 4. My unit would be moles per liter, and remember that with K expressions, sometimes the unit isn't always apparent, but we're always dealing with concentration, and the standard is mole per liter. I'll bring this value into my pH calculation. So negative log of 6.78 times 10 to the power of negative 4. And I would get 3.17 as the pH. Now I want you to notice this was a buffer, and the pH was not 7. A lot of people have this misconception that a buffer has to keep the pH neutral. Incorrect. The buffer keeps the pH at a particular pH. It could be a very high pH, a very low pH, or a neutral pH. In the case of this particular buffer, the pH is maintained right around 3. Now, it kind of looks like I have 3 significant digits here, but I don't. Can someone remind me why that is the correct way to report my answer? Yeah, Chase? Okay, sure. I don't count the 3. And Chase, you want to tell me why I don't count the 3? You only count things that are after the decimal. It's a log scale. The 3 is really telling you the power of 10. So, oh, why do I call you Chase? I do it all the time. And it's not the first time where I call him Chase instead of Cash, and I know that's his name. Could we just call him Chase? It would make my life easier. Boomer? And why will we call him that? Am I being inappropriate by saying that? Oh, but where? That's what it's referring to? Because sometimes people want me to call them by nicknames and it means something sketchy, and I think that I'm saying something innocuous, but instead. Okay. Well, if that's the reason, then it's probably better if I call him Boomer, because I can't seem to call him by his actual name.